Hey everyone, and welcome. Today, we are going to crack one of the most powerful codes in all of mathematics, exponents. Yeah, I know they can look a little intimidating, but trust me, they're really just a genius shortcut for talking about huge ideas in a really simple way. By the time we're done here, you'll be speaking the language fluently. Let's jump in.
But before we get started, I want you to just look at something. You ever see expressions like this in a textbook and your brain just kind of shuts down for a second? You think, what is even happening here? It just looks like a total jumble of symbols and numbers.
Yeah, this thing right here. This looks like the final boss of the math chapter, doesn't it? But I promise you, by the end of this explainer, the logic behind this whole mess is going to be completely clear. To get there, though, we have to start right at the beginning.
So, Section 1, the foundation. Let's get down to it. What even is an exponent? Before we can start using the rules, we gotta know what it is we're actually working with.
Okay, so what is an exponent? It's simply a way to write down repeated multiplication. That's it. In an expression like x to the power of n, the x, the big number on the bottom, that's our base. And that little n floating up top, that's the exponent. It's just a tiny instruction telling you how many times to multiply the base by itself. It's shorthand. It's a piece of code.
All right, Section 2, the core rules. Every language has its own grammar, and exponents are no different. So let's learn the basic grammar of powers.
First up is the product law, and this is so important. This only works when you're multiplying two powers that have the exact same base. If they do, all you have to do is add their exponents together. Simple as that.
Take a look at this example from our source material. 3 to the 5th times 3 to the 8th. The base, the number 3, is the same for both. Perfect. So we just add the exponents, 5 and 8, and we get 3 to the 13th. Easy, right? But the really cool question is, why does this little shortcut work?
Let's just break it down. 3 to the 5th is literally just 5 3's multiplied together, and 3 to the 8th is 8 3's multiplied together. So when you multiply those two things, you're just putting all of the 3's together in one long line. And how many are there in total? 13! The rule isn't magic, it's just a much faster way of counting.
Now let's move on to the next rule, and see how this all connects. This is the quotient law, and it's basically the exact opposite of what we just did. When you divide powers with the same base, you subtract the exponents. For example, if you've got 2 to the 12th divided by 2 to the 7th, you just subtract 7 from 12, and you get 2 to the 5th. I mean, it makes sense, right? Division is the inverse of multiplication, so it feels right that we do the inverse of adding exponents, which is subtracting them. Okay, one more core rule for you. This one's the power law. What happens when you have a power that's being raised to another power? Well, in this case, you multiply the exponents together. So if you have 3 to the 6th and that whole thing is being raised to the power of 2, you just multiply the exponents. 6 times 2 gives you 3 to the 12th. So when you see a power of a power, you multiply. All right, Section 3, the weird cases. We've got the basic grammar down. Now let's look at the couple of cases that can seem a little strange at first glance. Negative exponents and the zero exponent. But as you're about to see, they're actually perfectly logical. So what does a negative exponent even mean? It's actually pretty simple. It means take the reciprocal, and reciprocal is just a fancy word for flipping a fraction upside down. So a to the power of negative n is the exact same thing as 1 divided by a to the power of positive n. That little negative sign is just an instruction, telling you to move the power to the other side of the fraction line. Here's a really great way to think about it. If a positive exponent is a shortcut for repeated multiplication, then it makes sense that a negative exponent is a shortcut for repeated division. They are perfect opposites of each other. This leads to a pretty fascinating question then. We've covered positive numbers and we've covered negative numbers, but what happens when the exponent is 0? What could that possibly even mean? To figure this one out, we're not just going to memorize a new rule. We're going to use a rule we already know to discover the answer. Let's take this problem. 5 to the power of 3 divided by 5 to the power of 3. Now look at this. We can solve this problem in two totally different ways. First, let's use our quotient law. We subtract the exponents. 3 minus 3 is 0. So the answer is 5 to the power of 0. Okay. But we also know from basic arithmetic that any number divided by itself is just 1. 5 cubed is 125, and 125 divided by 125 is 1. So hold on.
We solved the same problem 2 ways, and we got 2 different-looking answers, 5 to the power of 0 and the number 1. Since they're both the answer to the same question, they must be equal. Therefore, 5 to the power of 0 has to be equal to 1. This isn't some random rule. It's a logical conclusion that comes straight from the laws we already established. Any non-zero number raised to the power of 0 is always 1.
Okay, section 4, putting it all together. You've learned the code, you know the grammar. Now let's put our new skills to the test and solve a problem step by step. Here's our problem, straight from the source text. We have a fraction, -3/2, raised to the -3rd power, and that whole thing is then squared. It looks like a lot, I know, but we just need to apply the rules one at a time. Okay, first step. We have a power being raised to another power. What rule is that? That's the power law. And what does it tell us to do? Multiply the exponents. So -3 times 2 gives us -6. And just like that, our problem is already so much simpler. It's now just -3/2 to the power of -6.
Next up, we have to deal with that negative exponent. And what does a negative exponent tell us to do? Take the reciprocal. It tells us to flip the fraction. So -3/2 becomes -2/3. And this is the critical part. That action makes our exponent positive.
And from here, it's just calculation. We raise both the numerator and the denominator to the 6th power. 2 to the 6th is 64, and 3 to the 6th is 729. And since our exponent, 6, is an even number, the negative result becomes positive. And there it is. That's our answer. By just applying the rules one by one, that really complex-looking problem just became totally manageable.
So we went all the way from a basic definition to solving a tricky multi-step problem. You've seen that exponents aren't just some random rules to memorize. They are a logical, powerful code for describing the world around us. So the only real question left is, now that you can read the code, what will you build with it?